Hello everyone. So today we are here to solve this lead code problem 72 edit distance. So let's read the description first and then try to solve it. Okay. So we have been given two strings, word1 and word2. Return the minimum number of operations required to convert word1 to word2. Okay. And then you have the following three operations permitted on a word: insert a character, delete a character, replace a character. Okay. Let's look at the example. So we have word 1, that is horse, and we have word 2, that is rose, and then output is 3. Let's see why is it 3. Explanation. Horse can be converted, replace H with R. So it becomes RO, RSE. And then remove R, it becomes rose to rose, and then remove E, it becomes ROS. Okay. Let's look at the other example. We have word 1 intention and the other word that is execution. Output 5. Let's look at the explanation. Intention to remove T. Remove T. Which T? This T. And then it becomes initial. And then we replace I with E. It becomes initial. Replace N with X. It becomes in extension. And then replace N with C. Become execution, and then replace N with C, it becomes execution, and insert E becomes execution. Okay, length of words is less than equals to 500 and consists of lowercase English letters only. Let's try to think like how we can do it and then try to implement a brute force solution at least, and then we can try to improve upon that. Let's try to do one example uh, by ourselves so we can understand it better. So we have word 1, HORSE, HORSE, and if we replace H with R, it becomes RSE, and if we replace this R with S, it becomes ROS, ROSSE, and then if we remove remaining letters, it becomes ROS, S, and ROS. So it takes 1, 2, 3, 4. Replace, remove, remove, remove. But what we could have done is we could have RORSE instead of like doing this replace. We could have done this and then ROS. We get ROS and then remove the last if. So it's ROS. Okay. Let's look at the other example. I'm not able to figure out how I can approach it yet. Maybe we will have to use some sort of backtracking since it forms like a decision tree. Either we can insert, either we can delete or replace. So maybe we can have some sort of decision tree that will be like char, um, insert, delete, replace. Then this will have insert, delete, replace, and then this will also have insert, delete, replace, and then this will also have insert, delete, replace. So maybe we will have a decision tree, something like this, that way. And when we come across a solution where word 1 matches word 2, what we do is we simply like keep track of the distance, and when the distance matches, like when the distance is less than the earlier computed distance, we update it, and in the end we return this distance. um, yeah, let's see. So for this example, let's look at it again. Word 1 was horse. Okay, so we needed an R. What we could have done is the only option was to like insert and this would have become R H O R S E, or delete, delete would be O R S E, or update, and this would have been R O R S E. And then in this case we reach second. So what we do is if second matches, H matches, O it doesn't match, then we um like insert O R O H O R S E in this case, or we delete H, it becomes R O R S E, or we update H, it becomes R O O R S E. And then again this, let's take this one, or just keep going down to this one, becomes R O S H O R S E. And then we will have to like delete these. Maybe more efficient will be if we don't, instead of inserting, if there are characters left, maybe we can update, but then it won't be considering it for the next position. Yeah, right. Let's see if we can implement it using um, backtracking. Maybe we will require a helper function, and result, let result equals to infinity, we have to minimize it. Also, the length can be 0. So if word1 length, if word1 dot length equals to 0, so we return word2 dot length, since you will have to insert that many characters. And if word2 length is 0, then we will have to return word1 dot length, since we will have to delete all the characters in the word1. So that many operations. So that will be our edge case, and then for result we define our function that backtrack or simply traverse equals to this, and then we will pass our index here, and let's look at the base case. Base case will be if the word matches, if, and we will have to keep word 1 like what it is right now, or simply word. If word equals to word 2, then what we do is we update the length result equals to math dot min of word dot length or result. It's not word dot length, it's actually operations. So we will have to keep track of ops as well. Ops. So we will increment this ops every time. If that's the case, we do this and return. In the end, we so here what we do is what we are doing here is we are taking one, and then we are taking one character of H and then matching it with the character of that. What we can do, instead of doing this, we do word dot starts with word1. Okay, in this way we will be handling these cases, and what we do is we take ops plus word 2 dot length minus word dot length, since we are reducing this number. These are the number of operations for deleting a character. Okay, now what we have to do is we have to call traverse with word empty ops 0 index 0. Okay, and what this will do is this will come here, and then this will like traverse word Ops will be ops plus 1, index will be index plus 1. So this index is the index of the word 2. So here what we do is we insert. So let's first check if um, word index equals to word 2 index. If it's already equal, we don't have to insert or delete. We simply proceed to the next step. Mobs is not plus 1. Word is word plus word 2. Um, no, not this, but word 1. If word 1 index is equal to word 2 index, then we go word plus word 2 index, ops and index plus 1. Otherwise, what we do is else we traverse over to the next character with insert. We insert it. So we append the character of word 2. Ops is increased since we are inserting, and index is increased as well. And index, let's keep two indexes, one for word 2 and one for word 1. Index 2, or simply j and I. J is the index of word 2 and I for word 1. So word 1 I, word 2 j. So this will be I plus 1 as well as j plus 1. This will be, since it's insert, I j plus 1. This will be 0, 0. This is insert, and then we have update. Update will be word plus this, and then ops moves to ops plus 1. I moves, since this is update, so we move to next here, and j is also j plus 1. Update, and then we have delete. Delete will be word plus 2, ops plus 1. I is also moved, and j is also moved. For in case of delete, we ignore this, and without appending, we move to next, and then check again. Okay, once this is done, we return result. Okay, let's see if this works. Index is not defined. You are right. We have j, they also. What it is, allocation failure. I think we are doing something wrong. Let's look at the code again, and let's do a try run, which we should have done beforehand, but since we didn't do it in the Earlier, uh, let's do it now. Okay, let's do it for this. So we have word 1 is horse, word 2 is rose, and our word is empty, and indexes ops is 0, I is 0, j is 0. Okay, then um, we go here and call traverse with empty 0, 0, 0. Word starts with word 2. No, since it's empty, we do nothing. And then we move to next word 1 I equals to word 2 j. Word 1 I 0. H equals R. No, it doesn't. So what we do is we go to else, and we have three statements, one for insert, one for update, one for delete. What we do first is insert um, we insert word plus word to j. Okay, j was 0, and we insert word plus word to j, that is r. Ops is increased to 1, and j is increased to j plus 1, 1. Then we move again, come here, and again we our word doesn't start with 2. We come here and we see that word 1 I, that is H. Word 1 I, that is H. H doesn't start with H is not equals to R O, so we do nothing. We come back here, we insert, and increase the operations to insert O, J is incremented, and then again we come here and we again we insert this time S, ops is 3, J is 3, and then we come here and word starts with um, our word starts with a word 2. Yeah, right, word is word 2 now, and actually maybe we can do word equals to word 2. Then what happened here is ops plus 1. So what we are doing is word dot length, or ops plus word 2 dot length minus word dot length. This will always come as some minimum. You are not, we are doing something wrong there. Maybe you are missing on something. In this case, this will be Ross. This will be Ross. I was still at 0, and I was still at 0. Maybe we will have, maybe we can use this these indexes to like find out the operations remaining. Since I is at 0, we will have the remaining string left. So this will be like ops plus word 2 dot length minus I plus 1, since it's 0 indexed. If we have traversed this whole string, then that means I will be equals to word 2 dot length minus 1. Actually, not word 2, but word 1 dot length, since we are comparing this. And this will be word dot length. No, this will be result. Result ops plus word 1 dot length minus 1 plus minus I plus 1. Okay, that looks good. But why did it fail? Delete. Word dot starts with. Let's look at it. Let's try to run it again. Maybe we can add some um, let's try to run it on simpler test case. Um, it's breaking. Maybe it keeps on calling and it's not reaching here, so it's not terminating. Word dot starts with. This is the issue, I think. Mhm. It could have been a simple update, but it printed output as 2. Let's um, add a console statement here. Word ops I j. Word is empty. 000 v101. 101. We added a v, so ops is 1 now. So it starts with. It's not working as expected. Let's keep debugging. In here, 101 math dot min of result or ops plus word 1 dot length minus I plus 1. Console dot log ops word 1 dot length I ops is 1, word 1 dot length is 1, I is 0. That is 1 I plus 1. Let's make it I plus 1. So this is 1 1 1 plus ops plus this minus this. So that is only 1. Then again here 1 plus 1, 1 plus 1 minus 2, that is 0. This is 3, this is 2. Like this. Ops is 1. Word 1 dot length is 1. Okay, reset test cases. Let's see. Error. Hmm. Four, 3. Yeah, right, since we didn't use the delete, but this delete is causing some issues. Yeah, right. We will have to add this check if it goes beyond um then we cannot go further. So if I actually this will be added here if I is already greater than um word 1 dot length, maybe we can make it like this. If it's less than, only then it will go. Same here. If it's update, so we require I to be less than its insert, we can insert as it is. Maximum call stack exceeded. Okay, I should be less than word 1 dot length. These two, or only for this. Mm, I think we require an iterative solution, maybe. Maybe let's try to solve it. Try run it. Horse, we take horse, word is not equals to 2, so we come here, and then we have word I equals to word I is not equal to a rows. So we have this insert. So insert will have j increased, and word will be r. Then again insert o. Then again insert. We have j equals to 3 ros. Then we have word equals to word 2, and we do this. We return from here, and after returning, come back here and do this traverse. Hmm. We are not doing this logic correctly. We were supposed to be doing a backtrack, but after inserting this ROS, we should be backtracking and taking this S out and then updating this H with S, but we don't have access to it anymore. So maybe we should correct this now. We have to somehow like solve this. Okay, yeah, right. This word will be in that case. Word will be RO. Yeah, right. Rate speed will be RO, and then we update this word um, H with J. So we have ORSE left, and ops are 3, and J is 3. We come here, it matches, right? We return, comes here, ops is again 2, 2, RO, and then takes out this H, deletes, and we have O, and it doesn't match. It goes here again, does the same thing. It inserts, matches, updates, matches, deletes, doesn't match, deletes, doesn't match, deletes, doesn't match. But it should be only deleting until there is something to delete. If there is nothing to delete, then it should not delete anymore, right? Same is the case with update. If there is an there is a variable to update, only then it can update. Otherwise, it cannot update. And for insert, it can insert whenever, wherever. traverse, 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 traverse. Hmm. Okay. Okay, so I did some drawings on my paper and I came to know that we don't require this word and we can take it out. So we take it out from all of these places. Now what we can do is we can simply keep track of uh, the indexes of word 1 and word 2. Okay, and here what we are doing is we are traversing with ops is initially 0 and I plus 1 and word index of word 1 is 0, index of word 2 is 0. What we will do is we will start with matching this R with this, and if it matches, if word 1 I matches word 2 J, then we simply move to the next character of I and next character of J. And if it doesn't match, then what we do is we increase the operation count, and for in the case of insert, we since we know that we no longer have to match this, since we will simply insert this at this location, so we will still match H with R with O, so that is J plus 1. In the case of update, we will be updating this H with R, and here we will match R with R, and so we will move to O second, so that is I plus 1 J plus 1. In case of delete, we will be deleting this H, and again we'll match this with this J, so this J will be uh, J simply, and then this is it. And here when we know that I is equals to word 1 dot length, that is the word 1 has ended, or J is equals to word 2 dot length, that is the word 2 has ended, then what we do is we calculate the number of operations. So number of operations will be total operations until now plus remaining chars of word 1 or word 2. So if both these were of equal length and they matched completely, then this will be 0. Otherwise, we'll be having the difference to add. Okay, so this will be like word 1 dot length minus I, and this plus word 2 dot length minus J, and this will be set in result, and we will be like keeping track of the minimum result. Let's see if this works. Yeah, it looks good. Let's try to submit it. Complexity is going to be huge since, yeah, right, it it got TLE, since we are doing recursive calls, and this is like 3 recursive calls and n times, so it will be um, AC of 3 raised to power n. So that is huge. Okay. Um, Let's see how we can optimize it. Maybe we can use a memo or something that will keep track of these I and j. Okay, so since it got up TLE, maybe we can use memoization and save some cost here. Um, let's see how will this work. We can have a set let um, cache equals to save, and in here what we do is um, let min insert, let min update, let min delete, let min ops is since we are adding one here, so this will be 1 plus math dot min of this, this, and this, and in the end of this function we can return main ops, and in here we can take it out and instead return this directly main ops. Okay, main ops, we will have to define it outside. Let main ops, and we can remove this. We are slightly changing the structure, and in here we return math dot max of so we have to return the max of these. So one of this will be 0 and the other won't be 0. So this should work. Let's copy this, and if it's in cache, if let's remove this, dollar $I hash $J, this will be like this. In cache we return cache, let G equals to this, otherwise we set this and return. Okay, let's try to run it. We forgot to change this signature. Nan. Hmm. Okay, we are still getting nan. Return math dot max of word one dot length. Word one dot length minus I. Let's try to console log our cache. Cache is empty. Why is our cache empty? In this case, we are not doing any uh, additions or anything, so we did this min ops like this. Okay, looks good. Did it come here? Let's see if we are even using this cache or not. Yeah, right. We are using this cache in the intermediate intervals. Let's try to submit it. Okay, yeah, it worked. And we used memoization and recursion, and the time complexity has been reduced drastically from 3 raised to power n to ONM. Okay, that's all. Thank you. Bye bye.